This is our third class. We have covered some ground on the viscosity of glass-forming liquids. And the material will be very important to understand relaxation phenomena and also crystallization phenomena, which we'll be dealing with in the next classes. Today, we'll talk about relaxation and also about the definition of glass. Since this is a vitreous or glassy state course, we have to understand what glass is. So the topics for today will be isostructural viscosity, which I just mentioned before, but this is important to understand relaxation because we are interested in relaxation below the fictive temperature, or in practical terms, below the TG of a given glass. And then, isostructural will provide the basis for relaxation, glass transition, and finally, towards the end of the class, we'll discuss a modern, updated definition of glass or glasses. Right. And then, when we finish, we'll talk about your homework. I know I gave you a tough homework, but we'll talk about that later on. All right. We have seen several times this plot, the enthalpy versus temperature for a material going from the liquid state to the supercooled liquid and finally to the glassy state. And today we are going, in the end, to come back here to use three concepts to understand the definition of glass. One concept is relaxation. This is relaxation. Any glass which is heated at a certain temperature and hold at that temperature for some time will relax to the supercooled liquid state. So the glass is unstable against relaxation. It will spontaneously relax. There is no thermodynamic barrier. There's just a kinetic barrier. And then, after it reaches the supercooled liquid state, it will continue its path towards the crystal phase and then will crystallize. So this is unstable against the supercooled liquid, and the supercooled liquid is metastable against the crystal. Then there is a thermodynamic barrier for nucleation of crystals. After nucleation starts, after the first nucleus, critical nucleus is formed, crystal growth takes over spontaneously. So we need to understand these phenomena here, the two phenomena, to come up with a rigorous definition of glass. Of course, there is a third important feature, that is structure, the structure of glasses. So relaxation, structure, and crystallization. Three different characteristics which will be involved in the definition of glass. Glass, of course, is a state of matter for which the intrinsic relaxation time, the structural relaxation time, is much larger than the time of the experiment. And the easier way to understand this process is to look at the plot here. Now, if we have a supercooled liquid and we cool it very fast, like pulling a fiber. If we want to make a fiber, the very thin fiber, we will lose heat to the ambient very fast. So have a fiber with a fictive, this is a fictive, called the fictive temperature, very high. And then the same liquid, the same composition, cooled much slower, like to produce a very large chunk of glass, a bowl of glass. Of course, the cooling rate, at least of the interior parts, will be much, much, much slower. So the same material can have two widely different fictive temperatures. Fictive temperature is the temperature where the structure is frozen for that experiment. And there is a difference, and people do not always realize there is a difference between the fictive temperature and the TG, the glass transition temperature that we measure in the lab. We normally do not measure these temperatures. We measure TG. So let's do an experiment, you know, a schematic experiment using this plot here. Let's assume that we have made a glass, big chunk of gas with a certain cooling rate. Of course, the cooling rate V2 is much slower than V1. So we have a glass here at room temperature. Then we start to heat this glass in a DSC. We are heating the glass, heating the glass, heating the glass, heating the glass. If we do it slowly, it will relax somewhere here. And this is the TG. So this TG may be close to TF2, but much lower than TF1. So TG may or may not be close to the real fictive temperature of the glass. If we take the same glass here and heat with a very, very fast heating rate, very, very fast, then the TG will be higher. It will come, and then relax. And the same process will take place with this other glass here, with the fiberglass. If we heat the fiberglass very, very fast, maybe it will come here and relax here, close to TF. Now, if we heat it very slowly, this glass very slowly, it will come here and then relax towards this position here. What I'm trying to say is that TG is close but not identical to the fictive temperature. It can be several degrees off, higher or lower, because TG, we measure normally TG on the heating path in the laboratory. We can also measure TG on the cooling path. If we measure TG on the cooling path, if we are coming here then from the supercooled liquid exactly with the same speed as we did to produce the fiber, the TG will be similar to TF1. If we do it on the cooling path with a much slower cooling rate, maybe the TG will be similar to this one. But in general, in the general case, TG is not identical to TF. That's why it's called fictive. It's not a real temperature. The fictive temperature is the temperature where the structure was frozen. And the glass memorizes TF. The structure has acquired a certain configuration. All the atoms and atomic groups have acquired a certain configuration which remembers the TF. I should say that there are ways to measure TF. And if any of you are interested, later on we can talk about this. But the idea I want to convey now for this class is that TF is where the glass was frozen. Tg depends on how we measure, depends on the heating rate, and depends if we do it on the heating path or on the cooling path. It's related. Tg is not here or here. It'll be somewhere here, but it can be 100 degrees off in practical terms of TF1 or TF2. And this is important. Not many people perceive the difference between the fictive temperature and the glass transition temperature. I'm going to talk more about this, but keep in mind this fictive temperature. This is a term invented by two in the 20s, many, many years ago, in the 30s or so. I'm going to give the full reference later. So, fictive temperature depends on the cooling path, on the thermal history, of the glass. Of course, I can take this glass here, heat it up here, and wait. If I wait here, keep the furnace at that temperature, it will relax, 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 up to here, or down to here. And this is the new TF. The new TF is here. So the TF changes during the relaxation process. The old TF was this one. The new TF is this one. And I can take this glass and relax this glass in the same temperature. And the newest TF of both will be the same, will be here. Or I can take this glass and relax for some time, not fully, and stop here. A relaxation process is a structural rearrangement which will stop when you cool down the sample, or if you come all the way down to the supercooled liquid. Then if you continue to heat up the glass, if you leave the glass piece, which now is no longer a glass, it's a supercooled liquid, in the furnace, it will further relax, forming a crystal. So the structure relaxes, in the end it crystallizes. This is the idea. This is important to follow the concepts we're going to discuss. Of course, if you recall the viscosity, log of viscosity versus temperature curve that we have discussed last class, these relaxation processes are normally studied here when the viscosity is 10 to 12, 13, 14 Pascal second or so. This is the range where one can normally measure the relaxation times. The relaxation times we have calculated last class. What's the relaxation time, typical relaxation time at the typical TG? We have done the calculations, 30 seconds or so at TG. Well, if we come 1 order of magnitude higher in a viscosity which is 1 order of magnitude higher, then we have an order of magnitude longer relaxation time, and so on. So this is the range. Well, of course, the liquid relaxes here also, but the relaxation times are very, very, very short, nanoseconds or so. Now, one key feature we are going to discuss today, because it's important for relaxation, is this isostructural viscosity. The log viscosity versus inverse of temperature. Even in this inverse of temperature scale is a curve, is no Arrhenian, but then becomes Arrhenian. below Tg. This is more or less the Tg. This is when the structure freezes, more or less. And then we have isostructural viscosities. Isostructural viscosity. To be rigorous, the structure freezes at Tf. But for practical purposes, in laboratory time scales, for practical glasses, Tg and Tf are not so different. But if you want to be rigorous, they are different, as I have shown in the previous slide. You know, if you compare a fiber with a normal cooled glass, they have completely different TFs. Now, if you measure their TGs of these two glasses with the same heating rate, then they will show more or less the same TG, because they will relax and will reach the same state. Below TG or TF, it becomes Arrhenian. You know, it no longer changes the derivative here, which is proportional to the activation enthalpy, no longer changes. It becomes constant. You know, the slope or the derivative here is constant. So we'll talk about this isostructural viscosity because we need it to understand the relaxation in this deep undercooled region. Okay, this is just a recap of the several viscosity equations that we have discussed in the previous two classes, but I'm going to focus now in the Adam-Gibbs equation of viscosity because it allows us to calculate the isostructural viscosity, and I'm going to show how. So, just a recap from last week. Okay, so we have already shown this equation using the Adam-Gibbs model of viscosity, which assume that there are certain regions in the glass, CRR, cooperatively rearranging regions, that become larger and larger as the temperature drops. And their expression relates the viscosity with the viscosity at very, very high temperatures, the exponential of an unknown parameter which is related to the activation enthalpy, the temperature, and the configuration and entropy of the liquid. And the configuration and entropy is a thermodynamic quantity which can be independently calculated. This is the nice feature of this equation. It relates a thermodynamic quantity which in principle can be independently estimated. This is the homework I gave you last week, with a kinetic property, which is viscosity. Now, another interesting feature, I'm not going to go through all the details because we have seen this last class, but a very important feature is that the configuration entropy explicitly depends on the this is the real temperature of study, but it also depends on that fictive temperature. It depends on where the glass was frozen. So we can rearrange the entropy, configuration entropy, as the configuration and entropy at Tf. Tf is the fictive temperature of the glass, plus an integral from Tf to T. T is the actual temperature we are studying, of the difference of specific heat of the liquid, the supercooled liquid, minus the specific heat of the glass. So this takes out the vibrational part and leaves only the configurational part. And we integrate this from TF to T. However, it's not so simple to calculate the configuration and entropy at TF. So an alternative form that I have sent to you a few days ago, 2 days ago, is this expression here. This expression was proposed by Pascal Richer, which is an expert in this field. And this, I gave you this expression. The configuration entropy depends on the actual temperature and on the fictive temperature. So it depends on the thermal history of the glass. So it's by V, I mean vitreous or glassy. V means vitreous or glassy. So the entropy of the glass at 0 Kelvin plus the difference, this integral here, which is the specific heat of the supercooled liquid, minus the specific heat of the glass, vitreous again, at TF divided by T. So this integral here will be negative because T is always larger than TF. So this term here will be negative. And then we have this part here. This part here. The entropy of the glass at 0 is given by this expression. The melting entropy, then the integral from 0 to Tm of the specific heat of the crystal. So we are going from here to here, the crystal, here to here, then the delta Sm is this part here. So this integral works this way. You integrate this part plus this part, and then you come down from the melting point down to TF. So we are coming down here, down to TF. Then we form a glass, plus from TF to 0 of the glass, because here we have the glass. So this is the logistics or the rationale of this integral. From 0 crystal to the melting point, this is the melting entropy, then the liquid from the melting point to TF, and then the glass from TF to 0. This is a nice way to estimate the configuration entropy. And as I told you, it depends on the temperature, because this is the temperature here, where you want to calculate it, but also depends on TF. See, TF appears here, TF appears here, TF is here. So you have to know the TF of the glass. For our exercise, we assume that TF is equal to TG. For practical cases, TF is similar to TG. So you replace TF by TG in your calculations. Of course, one needs data. So you have to search in the literature for the adopted glass. Each one of you have adopted one particular glass composition, stoichiometric glass. You have to find the specific heat of the crystal from 0 to Tm. And if there is not enough data, you have somehow to interpolate the available data and get a curve for that. And then you need the CP of the supercooled liquid from the melting point down to the glass transition temperature. Also need the specific heat of the glass from TG down to 0. So we need all these CPs, and then it's very easy. The calculation itself is very easy. It's integral of polynomial expressions. The hard part is to find the specific heat data and to interpolate this data properly. And I'm going to discuss later on, when we finish the formal class, how you can do that. This is the way to calculate. If you calculate this properly, it's very nice because then we can estimate the viscosity, since we have that. Even better than that, for a fixed TF, if TF is fixed, this is, you don't have to read all the text in this transparency because you're going to have access to the transparency, but my point is that if TF is fixed, the entropy part is fixed, and then we have a Arrhenian's expression, because this log is log of infinity plus a certain coefficient b divided by t, and since this is fixed, we can see that this is a Arrhenian equation. It becomes a straight line as we had predicted for the isostructural. The isostructural viscosity is Arrhenian. And it's Arrhenian because the TF does not change unless you wait some time and then it will change. But the overall result, log of viscosity, equilibrium viscosity, this is log of the viscosity 1 over T, equilibrium viscosity. If the TF is here, the configuration entropy is frozen, and then we have an isostructural viscosity. So our actual viscosity curve that the glass feels is this one. If this is TF, oops. If this is TF, this is 1 over T, TF. If we cool down the liquid, this is a supercooled liquid, with a much lower cooling rate, we have a different TF, so the isostructural viscosity will also change. The isostructural viscosity for another glass of the same composition, cooled slower, will be different. It will be different. And we can calculate this using this expression here. Then it only depends on the temperature, of course. Higher temperature, higher viscosity, but it becomes Arrhenian. You can also use the Maega equation. If you recall, one of the equations of the list is the so-called Maega equation, but that Maega equation was derived from the Adam-Gibbs equation. So you can also use that equation. The log of viscosity for a given TF is log of viscosity at very high temperatures. K is one of the terms of the Maega equation, and C is another term of the DeMA-UFSCar equation. So these are C, K, and log infinity are just the terms that you get from your fit when you fit equilibrium viscosity data. If you have equilibrium viscosity data, you fit the DeMA-UFSCar equation, 3-parameter DeMA-UFSCar equation, you get eta infinity, K, and C from the fit. And the same eta infinity, K, and C are used to calculate the isostructural viscosity. The only other parameter that you need is the fictive temperature, or TG, for all practical purposes, the TG. You come with the equilibrium and then iso or non-equilibrium. Iso or non-equilibrium. This is the equilibrium viscosity. So these are the two types of viscosity that we have to deal with, especially below the TF. We will be dealing with relaxation phenomena below TF. That's where we can measure the phenomenon in laboratory time scales. So what's relaxation? Relaxation is a time-dependent, irreversible process where a system changes its thermodynamic state towards an equilibrium situation. So in practical terms, if we stop here at this temperature and wait, this glass will relax until it reaches the equilibrium situation. So it changes its situation. This is relaxation. And this is a spontaneous process. You only need time. There's no thermodynamic barrier, just kinetics. Only need time. The lower the temperature and the higher the viscosity, the longer it takes. This is one example that we have measured here in the lab to prove to you that this is not a theoretical concept. This is something that one can measure in the lab. Which property can you follow? You can use the viscosity. You can measure the viscosity evolution with time, or the density, or the thermal expansion coefficient. Here in the lab, we have used refractive index. Refractive index, because the refractive index can be measured with a high accuracy to the fourth decimal place. So we use refractive index. We had a particular glass with diopsides, a calcium, magnesium, silica composition that we are interested. And we followed the relaxation at TG minus 30. So we had the laboratory TG of this glass. We equilibrated, this was the laboratory TG. We came down like 5 degrees below, waited for several hours to equilibrate the glass. So we went 5 degrees Celsius below the laboratory TG. He treated that glass. So the TF was now TG minus 5. Now we know the TF because we have heat treated for long enough so it equilibrated. So this is the new TF, different from the TF that the glass had when it was made. We did not know what was the TF because it depended on the cooling rate that we applied. But now we forced the glass to have a new TF. This new TF is TG, as measured in the lab, minus 5. And then we went TG minus 30. That means 25 degrees below the TF. And waited. See, waited. And the refractive index was changing, and then it equilibrated. So it took maybe 50,000 seconds 36,000 seconds is 10 hours, right? Yeah, 36,000 seconds is 10 hours. So let's say about 10 hours to equilibrate this glass 25 degrees below its TF, or 30 degrees below its laboratory TG. Now, another postdoc of ours worked with the same material at 50 degrees below TG. It took 6 months to relax, but it did. In 6 months, the glass, I don't have the curve here to show you, but it took 6 months to relax. So it's a highly exponential process because it took 10 hours at 30 degrees below TG, 6 months at 50 degrees below TG. It's highly exponential, but it relaxes. This is no, invention of some theoretician. This is an actual phenomenon. Glasses relax. And I'm emphasizing this feature of glasses because it's a key feature which has to be somehow embedded in the definition. By the end of the class, we have to show you a definition of glass. Relaxation is a phenomenon. You can measure this phenomenon. You can estimate this phenomenon. And another classical, this is a very classical example, Hara and Suetoshi, many years ago, have done a very nice experiment with soda lime silica glass, window glass. Soda lime silica is window or bottle glass, the most common glasses. His clever experiment was, okay, relaxation at 430 degrees Celsius. This is more or less here, close to the TG of the glass. You always work here because the time scales are practical. So he picked 530 degrees Celsius, which is a little bit below the actual laboratory TG of this glass. And first he equilibrated the glass at 500. The TF of this glass was 500. He left the glass many, many hours at 500. So we started here. And then started to follow the density of the glass as a function of time. So the density decayed at 530. Then he repeated the experiment for a glass which had been previously heat treated at 560. So the TF was higher than the equilibration temperature. And then it moved in this direction. And this relaxation process was faster than this one. If you look at this curve here, this is faster than that one. It's the same glass, heat treated at the same temperature with two different fictive temperatures. One was higher than the treatment temperature, the other one was lower. But the glass was the same. And the kinetics is different. This is one point. This relaxation process is not symmetrical. It's not symmetrical because it depends on TF. If TF is higher, for a higher TF, the relaxation process is faster than for a lower TF. So that somehow shows that if you recall the Adam-Gibbs equation and the configuration entropy, it depends on TF. And then if you plug in the viscosity, you see that the viscosity will depend on TF. I'm insisting this point because most people who are not in the glass research field do not perceive this key feature of glasses, relaxation. It's a very complex phenomenon, very complex. You see, it's non-symmetrical, and you see in a minute that's really stretched exponential. It's not pure exponential, as I'm going to show in a minute. So I'm just giving the phenomenology for the time being. And this is another experiment, but I can go through because it's similar. This experiment is very similar to those of Haren-Suetosh, but now changing the temperature or the viscosity, you know, for a viscosity of about 12.6 in log. It took only a few minutes to relax, and then the same glass at about 13.8 in log viscosity, it takes much longer. So it repeated the Haren-Suetosh's experiment, changing now the heat treatment temperature and showing that it takes a short time to relax at a low viscosity, a much longer time at higher viscosity, as expected. Okay, so let's then try to follow this cathedral glass idea because it illustrates the relaxation phenomenon. My question to you now is, what happens now if we come here well below the TG or TF of the glass? Say the TF or the laboratory TG of a soda lime silica glass is 550 degrees Celsius or so, more or less. 550 degrees Celsius. Now, we move down to 50 degrees Celsius. So it's a 500 degrees Celsius below TG or so. 500 degrees Celsius below TG. How long it takes to relax? First question, will it relax? If it does, how long it takes? So we have then tried to answer that question because many books and encyclopedia and textbooks and scientific papers mention the fact that medieval cathedral glasses are thicker at the bottom parts than in the upper parts. And that could be a proof that those glasses have, you know, really, they flew along 500, 1,000 years. So my question to you now, do you think 1,000 years is enough for a glass to flow or not? We now can calculate. If we have these isostructural viscosity curves, they're Arrhenian, so we can extrapolate down to room temperature and estimate these relaxation times. Let's do this exercise now. Estimate relaxation times at room temperature. I have a short video. Let's see if this short video works.
One of the more interesting is that glass itself is a viscous fluid. A very, very viscous fluid. In fact, glass is so viscous, it takes centuries to flow. To flow downward through time and space, where it settles along the eventually thicker bottom of the pane. Glass is so viscous that it seems solid indeed, and even rings and resonates.
So at some stage, he said, it settles at the thicker bottoms of the planes, you know. So this idea of medieval cathedral glasses flowing is widespread. So let's test this. Let's test the idea. Do they flow? Or did they flow in 500 or 1,000 years? The first attempt we did, published in 1998, we have used a model glass. Why GeO2? Because GeO2 is one of the few strong glasses. If it's a strong glass, The log of eta versus 1 over t plot will be almost linear. For strong glasses, their viscosity curves are not curved. So if they're linear, one can extrapolate. Data are normally collected here, but we can extrapolate them down to room temperature and have an estimate of the viscosity at room temperature. That's why we have used this model glass. Another feature is because the TG of GO2 glass is 550, very similar to the TG of cathedral glasses. So this is not a cathedral glass, this is a very expensive glass, but has a TG very similar to cathedral glasses in a linear viscosity curve. So a very rough estimate was done with GO2 glass, and then we estimated the typical relaxation time at room temperature. It was 10 to the 32 years. You know that an estimate of the average relaxation time is the viscosity divided by the shear modulus. Well, 10 to the power 32 is very interesting because does glass relax? The answer is yes, but you have to wait 10 to the 32 years. So they have not relaxed in 1,000 years. But some people read the article and say, well, okay, but this is not soda lime silica glass. This is a Germania glass. The only similarity is that the TG is very similar. So we had another paper that this article had a huge impact, huge impact in the literature, and even one of the editors of the Science magazine called me and spoke with me for 40 minutes about the calculations and so on of these cathedral glass papers. But many people have read the article and said, oh, there's a big flaw there because GO2 glass is not soda lime silica glass. So we decided to work with soda lime silica glass, but another question arose. Maybe the compositions of medieval glasses are completely different from soda lime silica glasses. Luckily, in this paper here, Dr. Miller and collaborators have analyzed 300 medieval glasses. They have collected for many years. It took them many years to collect throughout Europe, in many countries in Europe, different samples of medieval glasses of different ages and different sources and different raw materials. And you see that indeed the composition has the same major elements of modern cathedral glasses: silica, sodium oxide, calcium oxide, alumina, potassium oxide, magnesium oxide, and some impurities. These medieval glasses vary widely, but they have the same elements. These are the most common elements on the Earth anyway, but very widely. So one might say that, well, maybe some of these glasses have much lower viscosity than the typical modern glasses. However, this is the key feature, and that needs a lot of knowledge. If any of these glasses had a much lower viscosity, they should have a lot of question to you. Which type of elements would lower the viscosity? They should be rich in which type of elements or oxides? Alkali. they should be very rich in alkali, like potassium oxide or sodium oxide or calcium oxide or alkaline layers. If they were very rich, like 30%, 40% of these alkalis, what would be the chemical durability of these glasses? Very, very, very low. They would not have survived for 1,000 years. So this is a key step that needs knowledge, but hey, guys, okay, it's possible that some of these glasses have a lot of alkali, but their chemical durability will be extremely poor. They would not be adequate for cathedral glass. So the cathedral glasses that survived for 1,000 years must be similar somehow to these, more or less. Otherwise, they would not have survived. With that rationale in mind, which took us some time to realize, then we looked for many data points for modern. This is modern soda lime window glasses. You know, okay, it can vary by like 1 order of magnitude. From one glass to the other, you see this is more or less 1 order of magnitude. And there's more than 50 compositions here. But luckily, one author had measured the isostructural viscosity. See, this is TG here, and he had isostructural viscosity data. So we just fitted that Adam-Gibbs equation here, extrapolated down to room temperature. This is the idea. Had data, isoviscosity, with some data points. We had only some data points here. So we had a few data points here, and then we extrapolated down. This is room temperature. So the relaxation process is like going from here to the extrapolated value of the equilibrium viscosity. This is non-equilibrium. This is equilibrium. This is the process. However, why relaxation is complicated? If I use this viscosity, fine, but after 1 year, the viscosity will be here. After another year, the viscosity will be here. After 10,000 years, it will be here. After 100,000 years, it will be here. So the viscosity is changing. The relaxation process also changes the viscosity. So which one can we use to estimate the relaxation time? The average relaxation time for an estimate is just the viscosity divided by the shear modulus. But which viscosity? Should I use this one? Should I use that one? Some mixture? It's another problem. So, second problem. Since the data points were here, you know, we had data points here, any error in these data points, the extrapolation could be here or could be here. You know that extrapolations are very, very, very dangerous. They strongly depend on the quality of the data points here. And also to measure isostructural viscosity is very, very, very tricky. Why? It's very complicated to measure isostructural viscosity. You have heard my arguments before about relaxation. So my question to you is, and then I want the camera working in these guys because I want to hear their question. Why is it difficult to measure isostructural viscosity?
Because you have different amounts of relaxation very close to TG?
Because it relaxes. it relaxes. So if we are here, it's very difficult because it will take 200 years to relax, and you cannot measure. The value is too high. The value is too high. If we are here, the value is okay, but it's relaxing during the measurement. During the measurement. So you have to devise some special way to get viscosity data in a very short time before the glass relaxes. But this is impossible. So there's always a certain amount of relaxation. I'm saying all this to convince you that there's some data here, but it's not completely reliable data because of these difficulties. And then we have to use this data to extrapolate. And the extrapolation could be here, and this is log. This is log. So I can have many orders of magnitude error in the extrapolated value. And the third problem, which viscosity can I use to estimate the relaxation time? We could use this value here, but this is an upper bound. I could use this value here, but this is a lower bound. And that's what we did. Let's at least use this value to have a lower bound. In other words, the relaxation times estimated using isostructural viscosity will be less than the actual relaxation time. Why? Well, because the viscosity will be increasing. Relax a little bit, the viscosity is higher, so the process will be slower, and then relax a little bit more, the viscosity will be even higher, the process will be even slower. Anyway, it's some kind of average viscosity somewhere here is the correct one, but which one? So we have used this value for an estimate of the lower bound, and our estimate for the lower bound was, well, we did with Professor Gupta in American Journal of Physics 1999, so this is this second article, now using a soda lime silica glass, no longer GeO2 glass, and we use this value here of isostructural viscosity and a typical modern window glass. And the time was, oh, before, just a second, before I give you the result, just before I give you the result, I'm going to stop for a second to say that there are several relaxation models. One is the classical Kourosh relaxation model, which uses a single value of viscosity, but more accepted modern relaxation models, and I'm going briefly to talk about two, the MAP by Mauro, Allen, and Potuzak, published not long ago, 2009, and then they have some other papers improving somehow this model, but this is the basic equation, says that the viscosity as a function of time, and now you know that function of temperature, I'm sorry, a function of the actual, this is the actual temperature, and this is TF of that particular glass, is X times the equilibrium viscosity. This is the equilibrium viscosity, and 1 minus X, the non-equilibrium viscosity. Is like a mixture of, for a certain temperature, a mixture between the non-equilibrium and the equilibrium viscosity. And X can vary, when X is 0, you are dealing with only non-equilibrium viscosity. This is the limit in the very beginning of the process, X is 0. In the very end of the process, X is 1. So this part is over, we are reaching this. Somewhere in between, X is varying. So it's a balance between equilibrium, non-equilibrium, equilibrium, non-equilibrium. And this is, I'm not giving the final equation here, but this equation has 7 unknown parameters in the end. 3 unknown parameters from the equilibrium viscosity. We have seen these 3 unknown parameters fitting, and 4 unknown parameters of the non-equilibrium viscosity makes 7 fitting parameters. There's another older equation by two Narayana-Swamy and Monihan, TNM, two Narayana-Swamy, Monihan, and two is the person who came up with this denomination fictive temperature, TF, 1946, a very classical paper, viscosity and extraordinary heat effects in glass. Anyway, the same idea here. In the tau, the relaxation time, again, as a function of temperature and TF, depends on some x and 1 minus x. This is to show you that the same idea is x and 1 minus x, x will be changing from time to time, and you start here and end up there. So they both use this variable, this is to account for the variable viscosity during the relaxation period. I'm not going to discuss any longer these two models. There are even others. They're all complicated, but they fit well. They both fit reasonably well relaxation data. People do relaxation data at below TF, and they fit the relaxation data with one of these two models and some others. But I wanted to show you this to bring up this concept that the viscosity is changing from x0 to x1. The viscosity is changing. That's why it's so complicated to really understand and to model the relaxation process. But it's a key feature of the glassy state. So now, what's the result of our calculations just using the isostructural viscosity? I mean, a lower bound for the relaxation time. And again, we use the Adam-Gibbs model of viscosity, which can be written in several ways, but this is a way with a fixed TF, and we assumed that the fictive temperature of a window glass is TG. And this is a very nice assumption. Why the fictive is TG? Because a real glass has to be annealed. If you don't anneal a real glass, it will break. If you anneal properly a glass, the new TF is equal to the annealing temperature. And the annealing temperature is close to TG. So it's not bad to assume that the TF of all these glasses is more or less their TGs, because they have been annealed. So we took TG and we then fitted the experimental points from Mazurin. Mazurin had a few, 2 or 3 data points of isostructural viscosity using the Adam-Gibbs to be able to extrapolate here down to room temperature, 30 or 25 degrees Celsius. And the final result is 10 to the 24 years. Not as high as 10 to the 32 years that we had for GeO2, but still very, very long. Very, very long. Now, many people have worked and done other calculations on the viscous flow of medieval cathedral glasses. Remember, this is a lower bound because we use this value here. So the actual time could be even higher than this. But other people have done calculations and then to to summarize, I'm going to show the newest paper was published by a group of Corning Glass, John Mauro and co-authors. This is the famous Westminster Cathedral in London. Very nice cathedral. I have been 2 or 3 times to this cathedral. It's extremely nice. It has very nice stained glass windows in the UK. And the composition of this glass is a little bit different from the modern window glass. Some people have somehow a piece of glass was broken, so they had it analyzed, and the analyzed composition of the Westminster Abbey Cathedral in London was analyzed, and the result was published in the Journal of American Ceramic Society last month, 2017, by Özgür, John Mauro, Gu, and Olos. They have then calculated this isostructural viscosity for this particular real window glass, and this is the difference. Log viscosity, Pascal second, Tg over T, to put all of them in the same plot. The first estimate for Germania glass was 10 to the 40 or so at room temperature. Then our soda lime silica glass was 10 to the 30 or so, the viscosity. And there, Westminster Abbey glass, 10 to the 24 Pascal second. Smaller than ours. They had experimental data here. So they had one experiment here that they have done to be able to extrapolate the non-equilibrium viscosity using their MAP model. They use the MAP model, we use the Adam-Gibbs model here. They use the MAP model, so fitting their curve from the equilibrium viscosity to non-equilibrium using one data point. So this is one data point they had. And the final result is that the viscosity was lower than the value that we estimated, but still they calculated a maximum flow of 1 nanometer in 1 billion years. That would be a very nice project for an internship student, you know, to follow the relaxation process of a glass at room temperature. Some guys are so slow that they would enjoy, you know, to do this kind of measurements. This is a joke, of course, but thing is, still, glass flows, does glass flow at room temperature? Yes, it does, but it takes a long time. So why these cathedral glasses are thicker at the bottom parts? If they had no chance to flow, why they're thicker?
Because the thicker part they bring below just because it's more weight and they concentrate below.
Exactly. They were handmade. They were completely ununiform. So they used, the clever guys used to put the thicker parts at the bottom. However, there are reports, some museum guys have measured different cathedral glasses, and you find thicker parts all over the place. Sideways, upway, everywhere. Some thicker parts are at the bottom, but not all of them. So this is a nice, when I found that report, I was very glad, because this is another proof that it cannot flow. Of course, all these numbers are estimates. You see, even this one, they had one data point here, and the extrapolation was here. You know, if the data point was here, the extrapolation would be here. So it's always not only for to tackle this particular problem, but any problem where one has to do very, very long extrapolations, it's always uncertain. The uncertainty is very large. But the three calculations for three different materials and different techniques, they all go to the same direction. Glass flows, yes, but it takes a huge, huge, unmeasurable time. Okay, so they were handmade. All medieval glasses were handmade, and there are two techniques to do, but I'm not going to discuss how they are done. Very common expression to understand relaxation is the famous Kourosh expression. Exponential of minus t over the relaxation time to a power beta, where beta is something between 0.1 and 1. This is a stretched exponential. If beta is 1, then we have a pure exponential. But beta is normally, if you do a relaxation experiment and fit to this equation with two unknown parameters here, at different temperatures, you see that beta is less than 1. And this means that this is a stretched exponential. It's not a pure exponential. Coming back now to relaxation, a very, very famous problem regarding glass science, the fundamentals of glass science, or of the vitreous state, is the Cowman Paradox. Cowman was a researcher in Princeton, and in 1948, he came up with this idea. How I'm using the now entropy versus temperature plot. If we have a supercooled liquid, and then we cool it very, very fast, like a fiber, have a glass here. Now, even slower, we have a different glass here. What happens if the cooling rate is such that we come here? But it can be even lower. At some stage, it will come here. If the cooling rate is such that the supercooled liquid survives, at a certain stage, the entropy of the liquid will be equal to the entropy of the crystal. And this is the paradox. How come the entropy of the liquid can be equal to the entropy of the crystal? And this paradox arises because of this relaxation process. If we make a glass very fast, we have a glass and no paradox. But if we try to cool it extremely slowly, at some stage, the TF of the glass will be equal to this temperature here. This will be the TF, but the entropy equal to the crystal, so this is TK, K of Cowman. The Cowman temperature, the Cowman paradox. 1948, 350 papers have been published on this phenomenon, and none of them has been able to solve. This is still open. It's an open problem in glass science, and I like to share with you, because you're taking an advanced course on the fundamentals of glass state, so you have to know at least the phenomenology involved in the Cowman paradox. And then, for the Cowman paradox then, one has to do the following exercise. The excess entropy is the difference between the entropy of the supercooled liquid and the crystal. When the excess entropy is 0, we have TK. So we can calculate this TK. Since you have now been collecting CP data, you all be able to use the same data that you have been collecting to calculate the configuration and entropy to calculate now the excess entropy, just the difference between the entropy of the liquid and the crystal. And the excess entropy is 0 at the Cowman temperature. Now we need this delta Cp now is no longer the Cp of liquid minus the Cp of glass. It's Cp of liquid minus the Cp of crystal. The only problem is that there is no data below the Tg. So there is data for the liquid above Tg, but of course there is no data below Tg because then we have a glass. So you need to fit this part here. You know that the Cp at 0 Kelvin is 0. So you have this data point here that you force the data point in your fitting, and you have all this data here. You have to fit some equation. And there is no good theoretical model for that, unfortunately. There are a few expressions, but I'll leave this open to you. You have to fit some smooth curve. It'll be a smooth curve from here to here for the exercise. And then you can calculate. This is the heat of melting divided by the melting point is the entropy of melting. And from Tm down to T, you integrate the delta Cp dt when this integral goes to 0 or when this negative part of the integral is equal to the positive part, it will go to 0, and you have Tk. So you are searching for the temperature where the excess entropy is 0, and this temperature is Tk. Okay? And the plot then looks like this one. The liquid, the entropy of the liquid, the entropy of the crystal, they'll be equal at some point. And the real paradox is that if we extrapolate here, the entropy becomes 0 above 0 Kelvin. And that violates the third law of thermodynamics. This is the real paradox. It's not exactly there, but here. But let's calculate Tk. This is an important open issue in glass science, and I'd like you to be able to calculate because you've done already the hard part, that was to collect all the Cp data. The calculation is very easy. It's a simple integral.
Excuse me.
Yes.
We have a linear relation for the Cp of the liquid or the constant number, so we cannot extrapolate very well.
Yes, I know that. For some liquids, he is saying that for some liquids, the Cp is more or less like this.
Or linear.
Or linear. Yeah, or linear. But then, at some stage, you have to invent, for the exercise, there are better equations, but for the exercise, even if you have a linear here, you know that this data point is 0. So you have tried to fit something here, from here to here, until you reach this point here. So you have two parts. You do not need to have one equation. You can divide your equation in two parts. One part from 0 to Tg, which will be some polynomial like this, and then another part, from Tg to, the melting point. So you can have two polynomials, sometimes even three polynomials, because if you remember, we discussed yesterday, at 0, here at 0, you have to fit an expression that I have sent to you last night. No, last night it's one term expression here to the power t to the power 3 or something like that. So you may need three equations. One for the very low temperatures, one equation for this part, and then the linear equation for this part. And that's a difficulty that people dealing with this problem face. You know, the difficulty is that the supercooled liquid does not exist. It should exist if we are able to do a very slow cooling rate. But in real life, we are not. So we have a glass. Below TG, we have a glass. But we need this value to be able to extrapolate. This is only an exercise. To do this kind of calculations is very hard because of this uncertainty regarding this part. But there are papers in the literature. If you're going to do your thesis in this area, then I can give you better equations to fit this part. But it's not the purpose now. The purpose is that you are able to handle these things and see what happens. We are not going to publish these results. It's just an exercise, okay? So we did this for different materials, and like lithium disilicate. Some of you are working with lithium disilicate, and Elena, you are working now with lithium diborate. We have calculated, you can calculate also the TK for lithium disilicate and for lithium diborate. We have these values. And why we have these curves here? There is a large uncertainty in these calculations because they're integral. When you have an integral, you have a sum of errors. Each step, let's assume that you divide your integral from 1 degree Kelvin to 1 degree Kelvin. It's a sum, and then another sum, and then another sum. The errors sum up. This is an error propagation. You know, you have errors in the CP, you have also errors in the fitting, so these errors propagate. To do it properly, you have to estimate the errors, but I'm not going to ask you to estimate these errors. It's even more complicated, there's no point. Your problem now is to estimate TK. So you have three kind of homework to do, 3 different exercises. You did one that was to fit the viscosity data for your glasses with different equations. The second one was to calculate the configuration and entropy, and then the Adam-Gibbs, the Adam-Gibbs equation for viscosity. And the third one is then the Cowman temperature. But there will be no classes next week. I'll be traveling next week, so you have 2 full weeks, 2 extra full weeks to complete these 3 exercises, okay? Now, I promised that I was going to give you the definition of glass. And I'm going to skip some transparencies and give you, which I think is the best definition of glass. We have published this definition in this paper here in the Journal of Non-Crystalline Solids a month ago or so. And use a lot these concepts of relaxation, also concepts of glass structure, but we will have a separate class. I think next class will be glass structure in crystallization, which we will see later on. So I'm going to skip the structure part, the crystallization part, because we are going to see in very details those 2 parts and move directly to the definition. So let's move to the definition. You know, typical definitions of glasses are non-crystalline solids that show a glass transition, or amorphous solids that show a glass transition, that undergo a glass transition. There are many definitions of glass. My question to you is glass a solid? Do you think glass is a solid? This is structure part. I'm skipping all because we are going to return in further classes in nucleation, crystallization, these kind of things, and moving to the new definition of glass. And this is it. This is a easier definition, shorter definition. Glass is a non-equilibrium, non-crystalline state of matter. I believe you understand now that glass is non-equilibrium. You wait for some time, it relaxes. So it's non-equilibrium. It relaxes and then will crystallize, believe me. So it's a non-equilibrium. This is the key word you have to memorize. Then you can put together. Non-crystalline, of course, everybody knows this, that the structure is not arranged in that three-dimensional space, that appears solid on a short time scale, but continuously relax towards the liquid state. This is one type of shorter definition of glass. Non-equilibrium, non-crystalline material that continuously relax towards the equilibrium state. This relaxation, however, comprises two parts. First, there is the structural relaxation, and after it's finished, there's the relaxation towards the crystalline state. So a fuller, more comprehensive definition is, and you now can understand this definition, you in this class. Glass is a non-equilibrium, non-crystalline, condensed state of matter that shows a glass transition. The structure of glasses is similar to that of their parent supercooled liquids. Believe me, I'm going to show this next class. The structure is very similar. It was a liquid. This liquid went out of equilibrium, but the structure did not change, almost nothing. At a little bit above, a little bit below TF, it's the same. And they spontaneously relax towards the supercooled liquid state. However, their ultimate fate in the limit of very long times is to crystallize. So you don't have to memorize the whole structure of this phrase, but you have to memorize some keywords. Non-equilibrium, non-crystalline, relaxation, TG, crystallization. If you memorize these keywords, you can set up your own definition of glass, but they all have to be included so we know exactly about the nature of glasses. With that, I finish today's class. Unless you have some questions, we can try to answer. This is a very quiet class. Very quiet class. No questions.
I was curious with the Cowman Paradox. I thought I read in a paper, I think it was by John Moreau, that they showed in some very organic liquid or something that it actually did relax to the crystalline state, or came very close at 0 Kelvin. Do you know if it's a matter of the fact that we can't measure in this region, and that there are some things that actually do extrapolate to 0 at 0 K?
Yeah, I'm not aware of anybody who actually measured. If you find this paper, please forward it to me, and I'll be most interested in reading that paper. But to my knowledge, people extrapolate things, but we're not able to measure. But let's take a look, and then we can discuss next time.
I have a question about this ultimate fate that I don't understand very well. When you reach the supercooled liquid region, you say that you need a thermodynamic barrier to stop the nucleation.
Yes.
So, does it mean that you need like more than time to achieve the...
No, all right. No, you need a certain temperature, of course. You need to be at a certain temperature, and the combination of the temperature and the, I'm going to give classes on nucleation, and you see the thermodynamic barrier for nucleation is something like W star. This is the thermodynamic barrier. From the classical nucleation theory, W star is the work, W from work, the thermodynamic work that you have to do to form a critical size nucleus. This star means a critical size nucleus. This is proportional to some geometrical constant, which depends on the geometry of the crystal. The interfacial energy to the third power. This is the crystal liquid interfacial energy, because if you form a crystal, excuse me, inside a liquid, a new surface is formed. So you have a new, this is a positive contribution to the overall energy, and divided by the difference in free energy, the difference in free energy of this is the difference between the energy of the crystal and glass by unit volume. So, and then we have a KT, the Boltzmann constant and the actual temperature. So it's the balance, the balance of these two quantities is the thermodynamic barrier. If you need if the difference in free energy of the surface free energy between the crystal and the liquid is very high, it'll be almost impossible to form a nucleus. It's very low, it'll be easy to form a nucleus. So it's a balance between all these parameters. This is a thermodynamic barrier. And then there is a kinetic barrier also. As in the relaxation, there is no barrier. It's just a kinetic diffusion. Just a diffusion barrier. For nucleation, you have a thermodynamic part and a diffusion part. You have also a diffusion part. And I'm going to talk about this in 3 or 4 more classes, but diffusion and thermodynamics. Relaxation is only diffusion. It does not need to overcome any barrier. It's spontaneous, it starts immediately. I want to say that it will take time before you form the first nucleus. Here, when there's only kinetics, it takes 0 time. It starts to relax immediately. It takes long to fully relax, but any glass like this is relaxing. It's relaxing. After a few million years, I don't know, this will melt, will, wet the substrate. So this is I think, of course, this is our own definition. This is our own definition. Let's see if published last month, let's see if the glass community or the physics community will accept this definition. But this is, I think, the best definition so far. Thank you.